Welcome. This will be our last topic in work and energy. So, we've been talking about work, energy, and conservation of energy. If you need a second to pause the video and copy down the stuff that I've written on there so far, please go ahead and do that now. All right. So, the situation I've got outlined here is pretty simple. We got two cars that are going to race. We have my Porsche, because all teachers own Porsches, right? And it's a really nice, fast Porsche. And then you are driving an old Volkswagen Beetle, otherwise known as a Bug. This is like the 1960s version old Volkswagen Beetle. And for both vehicles, we're going to say that their mass is 1,000 kilograms each, which might be about right. And let's say they both start from rest, okay? And then the light turns green and we both floor it. All right, so my Porsche will go from 0 to 60 in about 5 seconds. Okay, now 60 miles per hour is about 30 meters per second. So our V final will be 30 meters per second. Okay. Your old Volkswagen Beetle, your Bug, it takes, let's say, 20 seconds to go from 0 to 60 miles per hour or 30 meters per second. All right, so first question. Which car did more work, or which engine did more work on their respective cars? So you might think that the Porsche did more work. It turns out it didn't, okay? So we have our conservation of energy equation here, and we're going to calculate the work done on both vehicles, okay? So both vehicles started from rest, so their kinetic energy was 0, they weren't moving. There's no change in height, so the gravitational potential energy was 0. And there's no springs here, so there's no elastic potential energy. So the work that we're going to calculate is the chemical potential energy from the gasoline that turns into kinetic energy. Okay. Now, when the cars are at the end of their motion, they're moving 30 meters per second. So they do have kinetic energy. And again, there's no change in height and there's no elastic energy. Okay. So work is simply equal to kinetic energy, okay? And if you'll recall, work equals, for kinetic energy, it's 1/2 mass velocity squared, okay? So which car had a bigger mass, the Porsche or the Volkswagen Beetle? Well, they both had the same mass. And which car reached a higher final velocity? Well, they both reached a higher final velocity, the same, 30 meters per second, okay? So it turns out both cars did the same amount of work. And as a matter of fact, we can calculate that. We got 1/2 times 1,000 times 30 squared. And if you do the math, you will get 450,000 joules of energy. So both cars did the same amount of work. However, there's something different about the cars, right? You pay a lot more money for a Porsche. Why do you pay a lot more money for a Porsche? Well, it's not the amount of work the car can do, it's how quickly the car can do the work, or more appropriately, the rate at which the car can do the work. And the rate at which something does work is called power, okay? So power, the equation for that is P is work over time, okay? So you might notice, even though both vehicles had the same amount of work done on them by their engines, the Porsche did the work in a lot less time. So if I make the bottom of this fraction smaller, the number itself gets bigger. Now, before we plug those numbers in, real quick for units, we know work is measured in joules, and we know time is usually measured in seconds. We call a joule per second a watt. So, I'm sure you've heard of watts before, like light bulbs or hair dryers. And that means exactly the same thing. But you have an 1800 watt hair dryer, it means it's using 1800 joules per second of energy, okay? So let's go ahead and do this calculation for our Porsche. So I'll do power of the Porsche. So that's work over time, which is 450,000 over 5 seconds. And you get 90,000 watts. Okay. Now, by the way, on a side note, that would be about 120 horsepower. Okay. 1 horsepower is 746 watts. So if you divide 90,000 by 746, you get about 120. The power of your beetle, your bug, is work over time. It's the same work. We had the same starting and final velocities and the same mass, but it took your beetle 20 seconds to do the same amount of work. It was slower, right? And if you do this calculation, you get 22,500 watts, which is about a quarter of 90,000. Or if you figure it out in horsepowers, it's about 30 horsepower. Okay. So even though both vehicles did the same amount of work, the power was quite different. The Porsche had 4 times the power of the Beetle. Okay. So that's the difference between work and power. Power is how quickly you do your work. Okay. Now I got a second example for you. Let's say we're lifting something, and you'll see some of these on the worksheet. Let's say in this case, there's 2 elevators. Let's say here's elevator 1, and it's got a bunch of people in it. Okay, bunch of people. All right, and let's say the total mass of the elevator and the people added together is 2,000 kilograms. And let's say the elevator is lifted 20 meters, and this takes 10 seconds. Okay. And let's say you have a second elevator and it's empty. And so its mass is only 1,000 kilograms. Okay. It's going to lift the same 20 meters, same distance, but this one's going to go much quicker. It's only going to take 4 seconds. Okay. So the first question is which elevator had more work done on it? And then the second question is which elevator had more power or required more power to lift it in the respective times. Okay. Oh, and by the way, the first time, for some reason, I just wrote seconds there. I didn't write the actual number. It's 10 seconds. Okay. All right. So for work, okay, I'll write out the conservation of energy equation again. So we got EK plus EG plus EE plus work equals EK plus EG plus EE. Okay. Well, let's start with there's no springs involved in any of this, so there's no elastic potential energy. We're going to assume the elevators are both traveling at a constant velocity as they're being lifted, so there's no change in velocity. So while there would be a number here and here, they're the same number. So these are going to cancel out because the velocity is not changing. Okay. And we're going to say that the beginning height, we're going to call that 0. So there's no gravitational potential energy at the beginning. And so what you end up with is a very simple equation. The work that's being done on the elevator is turning into gravitational potential energy. Now, by the way, this would be probably electrical energy turning into the gravitational potential energy. The elevator's probably got an electric motor. Okay. And the equation for gravitational potential energy is mgh. Okay. I'll call the left-hand elevator A, and let's call the right-hand elevator B. Okay. So for elevator A, the work done on A is mgh, which is 2,000 times 9.8 times 20. And if we do that, we get 392,000 joules. Okay. And then if I want to find the power, okay, that's the work done over time. Okay, and we'll call this the power of A, the first elevator. The work we just figured out, I'm not going to even rewrite, I'm just going to put an arrow here. And the time it took was 10 seconds. And if I take 392,000 divided by 10, I get 39,200 watts. Okay. For elevator B, it's the exact same calculations, we just have different numbers. So the work done on B is the mgh of B, which is 1,000 times 9.8 times 20, which is 196,000 joules. And the power delivered to B is the work of B over time, which is this number, which we don't need to rewrite. And the time was only 4 seconds. And when you divide those out, you get 49,000 watts. Okay. All right. So if I ask you which elevator had more work done on it, it's elevator A. It had 392,000 joules versus only 196,000 for elevator B. But if I ask you which elevator required more power, the answer is the elevator B. Elevator A only took 39,000 watts. Elevator B took 49,000 watts. Okay, and that was because of it went so much faster. It went so much quicker that it took more power to do it. Okay. Now, one last thing I'll mention, and this will be asked on your practice as well. Okay. Conceptual question. Let's say there are two people in a grocery store and they're lifting boxes to a high shelf from the floor. And both people are lifting the same boxes, same kind of boxes, same mass of boxes, and they're lifting them the same height. But person one lifts the box 20 boxes in 50 seconds. Person two lifts 15 boxes in 20 seconds. Okay. Saying two questions. Which person did more work and which person had more power? Okay. Well, this is like the elevator problem. The work that's being done is turning into mgh. Now, I didn't give you the m or the h, but what you can say is person one, they lifted 20 boxes, and person two only lifted 15 boxes. So everything else is the same. The G and the H and the mass of each box is all the same. So which person did more work? No, person one, they lifted more boxes, all right? But which one had more power? Well, power is work over time. For person one, they did 20 boxes. It took them 50 seconds, which should be 0.4. Now, this is not watts, okay? This is because we don't have G and H in there, but it's just a number. It's a ratio, okay? Person two, they lifted only 15 boxes, but they only did it in 20 seconds, and you get 0.75 for that. Now, again, these aren't in watts, but this is a relative comparison. So person two had almost twice the power of person one. Even though person two did less work, they did it so much more quickly that they have more power. Okay. So when you're answering questions about work and power, you have to look at how much work was done, and then also for power, how quickly they did it. Okay. All right. I hope that helps, and good luck on your last sheet.